My name is Madeline Morrell, and today I want to talk a little bit about thermochemical salt hydrates and how we can utilize these for not only energy storage within buildings, but then also dehumidification. So as we all know, buildings consume a lot of our energy. In fact, for residential and commercial buildings combined, around 50% of our energy consumption is attributed to thermal loads, such as space heating, air conditioning, water heating, you name it. Now, this is of major concern because by 2050, we're expecting to see around 50% of our global energy consumption being attributed to buildings. And in order to mitigate the effects of this growing demand due to the electrification of heat pumps, as well as the increased demand for cooling, we can incorporate more renewable energy systems into our grid. But what we see is that there is a mismatch between the supply that we're able to get due to these intermittent sources, as well as the demand that we have for buildings. These peak demands here at the end of the day versus the higher supply that we might see in the middle of the day when you have lots of solar and lots of wind. So in order to address the sensible or the temperature thermal loads, as well as the latent or the humidity thermal loads that we need for buildings, people have developed many various technologies and incorporated them into buildings. So for the thermal energy storage, we've seen a lot of sensible energy storage units, looking at hot water as well as cold storage. And then for dehumidification and addressing these latent loads in buildings, we have implemented desiccant dehumidification systems, such as liquid desiccants as well as sorbent desiccant wheels. But I want to propose, what if we could combine a system that would address both sensible and latent thermal loads simultaneously? So what I'm looking into is I'm investigating thermochemical salt hydrates. So why exactly? These are a reversible solid gas reaction wherein the operating gas is humid air or water vapor, and it reacts with a salt hydrate solid. So for thermal energy storage applications, they're really high energy density. They're also non-toxic, low-cost materials, and then for the reaction conditions, they operate at suitable temperatures for buildings. So how this would theoretically work is we're able to store this off-peak energy from the grid and use this to facilitate this endothermic reaction, which is what we call the dehydration or the charging reaction. And with this, you release water vapor out of your hydrated salt bed to create dehydrated salt. So this would be your charged thermal battery. With this, we usually operate at higher temperatures, so around 60 to 80 degrees Celsius, and at low vapor pressures for humidity. Then, when you're ready to utilize this energy later, we're able to reintroduce humidity or water vapor into our system, which facilitates an exothermic reaction known as the hydration or the discharging reaction. And then we're able to release this heat for building energy end uses. So for this operating condition, we usually look at around room temperature and cooler, and we operate at higher vapor pressures for our salts. Now, for pure salts, that's kind of what I discussed, but there are a lot of limitations, so I kind of want to discuss that. So for example, calcium chloride, this is a really low-cost salt at around $42 per kilogram, and it's also readily abundant, and it has a high theoretical energy density in comparison to some other thermochemical salt hydrates. So looking at around above 600 kilowatt hours per meter cubed as in comparison to these other forms. However, this has a lot of hydrothermal instabilities which make it hard to implement and incorporate into buildings. So instead of going through a direct solid-to-solid transition between the dehydrated and the hydrated phase, overhydration at really low relative humidities can actually cause this salt to form into a liquid solution. So we call this deliquescence. And then when you dehydrate this deliquesced liquid, it results in this agglomerated mess, sort of here, and this makes it really difficult to continue to use your thermal battery due to transport limitations with water vapor not being able to easily pass through your salt. So one of the things that we're looking at doing is incorporating these salt hydrates into porous matrices to help address the hygrothermal limitations that we see. So we have found mesoporous silica impregnated with this calcium chloride to be a really promising solution. So for a thermal storage application, we have shown that this is hygrothermally stable in the hydration-dehydration reaction for over 100 cycles, which is pretty significant, and this is at the material scale. And part of the benefit of using this mesoporous silica is that there's this nano-confinement effect within the porous walls of the silica, and it allows for deliquescence to still occur, so we're able to operate at higher humidities than we are with pure calcium chloride because of this capillary action where the deliquescence remains in the pores and there's no leakage. So you can kind of see here we're operating up to 80% relative humidity, and there is no leakage that we're seeing with our calcium chloride when it's impregnated in this salt. So the synthesis technique for this, what I have done is I'm able to impregnate using a wet impregnation technique. So I just create this salt solution with methanol, and then add my silica to it, and then allow it to separate over a span of 2 hours, allowing the salt to go into the pores of the silica. And then by dehydrating this solution, in order to get the methanol out, I'm able to achieve a dehydrated silica salt composite. So first I want to kind of start with the material level characterization, and we do this with TGA-DSC that is integrated with humidity control. So looking at its thermal energy storage capabilities, because it is in this host matrix, the volumetric energy density does decrease a little bit. So I wanted to look at different relative humidity conditions, and you can see that it's pretty thermally or hygrothermally stable with the energy density and the water uptake over just these 10 cycles, showing high promise here. And the volumetric energy density that we're getting for like around here for the 50 and 60% relative humidity is around 1,800 joules per gram, or 316 kilowatt hours per meter cubed. And this is pretty comparable to other TCMs, especially in their pure salt form, and it appears to be slightly higher than some commonly used PCMs that are being integrated and investigated. In addition to this, I've also used TGA-DSC to characterize the sorption isotherms, and I'm able to characterize these against commonly used sorbent desiccants. So you can see this performance is comparable to silica gels and zeolites that have been integrated into desiccant wheels. I will note that this is polyacrylamide lithium chloride solution, which has been like a hydrogel composites, and that's been looked into for a sorbent desiccant as well. And this appears to be higher. However, the benefit of the silica salt composite is that it reacts really quickly in comparison to these hydrogels, as it doesn't continuously take up water. So that's sort of a benefit of this material. So moving forward towards this integration into buildings, one of the things I wanted to investigate was how well would this work at a reactor scale, and what conditions, variations with the testing conditions, how would that affect the thermal and dehumidification performance that I'm seeing in my reactor. So these experiments are necessary to further characterize, and what I did is I did reactor scale experiments looking at a 5-hour discharge period, so that is the same as a C rate of around 1/5. So I wanted to ensure that it's able to discharge within a sufficient time frame for peak load shifting and shaping. So I've investigated these 3 different cases, looking at how operating parameters with my experimental tests would affect the reactor scale performance. So I used 50 grams of salt within my reactor test section, and then I just allowed for it to hydrate over a 15-hour time period to ensure full characterization, but I'm mostly focusing on the 5-hour discharge region. So I selected a base case of around 60% relative humidity and 10 liters per minute. And then I also varied the relative humidity, so keeping flow rate the same, but then decreasing the humidity just slightly to see what effects that would happen at the reactor scale. And then I also did the same thing with flow rate, where I kept the humidity conditions the same as this baseline case, except I slightly increased the flow rate to see what effects that would have on the thermal performance. As for experimental characterization at the reactor scale, I was interested in characterizing the maximum temperature lift that I was achieving within my reactor, as well as the thermal power output into the air that is leaving my reactor test section. In addition to this, I was also interested in the dehumidification capabilities of this reactor, so looking at the dehumidification capacity, so the difference between the inlet and the outlet's humidity ratios, as well as the effectiveness, so dividing this dehumidification capacity by the inlet humidity ratio. So in order to test these, I've developed this open system test bench. So with this, I'm able to operate at different relative humidities at room temperature. And so how it works is I just split building air into a wet line, which is able to create saturated relative humidity. as well as a dry line here on the bottom, and I'm able to recombine it then to get the mixed air at the humidity condition that I want, and then I can send it to my reactor test section here. Within the reactor test section, I have thermocouples to measure temperature lifts within the air and the salt bed, and I also have relative humidity and temperature sensors in the lines before and after the reactor so that I'm able to characterize the air temperature lift as well as the humidity uptake with my reactor test section. So this is what the device looks like. Pretty simple, just my two mass flow controllers here, and then my wet line would be the one on the top, and then my dry line would be the one on the bottom. And then I'm using LabVIEW in order to adjust the flow rate conditions for my mass flow controllers on the wet and dry lines respectively, and also ensure that the humidity that I'm supplying to my reactor here is in the conditions that I want for my tests. So the first test that I did, so this is my reactor. I have inlet air, humid air coming in from the top, and it passes through the silica salt bed here, and then it leaves on the bottom here. And here my thermocouples kind of scattered throughout the bed. It's about like 4 centimeters of the silica composite in the reactor itself, and this is about 15 centimeters in length. So the first test that I did was varying the relative humidity at a constant flow rate of 10 liters per minute. And what I saw was, even with this slight variation with the relative humidity, this can significantly affect the temperature lift, wherein the temperature lift is a little bit lower in comparison to the 60% relative humidity case. I also saw that this really affected the thermal power that I was achieving from the airstream. So due to this lower temperature lift, I see a 3 times nearly reduction in the maximum thermal power that I'm achieving from my reactor. And it begins to, like, I'm hardly getting anything really after this, like, 10-hour time frame out of this test section. So comparing this to the theoretical values that I was expecting to see based on the material level characterization, at 60% relative humidity, it's a lot closer at the gravimetric and volumetric energy density scale in comparison to the 50% relative humidity case. And also looking at this too, based on the thermodynamic limits based on the phase diagrams for calcium chloride, I was expecting a temperature lift of 17 degrees Celsius for the 60% case and 15 degrees Celsius for the 50%. And I saw both of them were slightly lower than what I was expecting to see based on theory. And then for the 60% case, we see that in this 5-hour discharge period, we're maintaining above 9 degrees Celsius constantly within our reactor test section, whereas the 50% with just a 10% relative humidity difference is only maintaining above 6 degrees Celsius. So this kind of shows that even slight variations when you're looking at your humidity conditions in the air can have significant impacts at the reactor scale of your material performance. So next thing I looked at was varying the flow rates and how that affected the thermal energy storage performance. So I kept relative humidity and temperature the same for both tests, and then I looked at flow rates of around 10 liters per minute and 15 liters per minute going into the reactor. So what I saw here was that the temperature with the 15 liter per minute case was slightly higher, and it kind of shifted the peak for the temperature lift to be a little bit shorter. So the reaction is progressing more quickly because there's more humid air coming into your reactor, so it's able to fully react to the constant regeneration and increase of humidity into your reactor system. And in addition to this, you also see this kind of effect with the thermal power, where there is a higher thermal power towards the beginning, and then it begins to level off sooner in comparison to the 10 liter per minute case. So also looking then at the expected temperature lifts. So based on theory, again, we were expecting around 17 degrees Celsius, and we actually did achieve that with the 15 liter per minute case at the very beginning of this reaction. And you see slight variations here with what is maintained over this 5-hour discharge period. So within 5 hours, for the 15 liter per minute, it's slightly higher, just because more of the reaction is happening during these first 5 hours in comparison to this due to the higher flow rate. And we also see over this 15-hour discharge period throughout the entire experiment, the energy density is also slightly higher at the gravimetric and volumetric energy density scales, which is what we were expecting because, again, we are supplying more humidity to our reactor. Lastly, I wanted to briefly kind of touch on the dehumidification performance of the system. So using the relative humidity sensors that I've incorporated into my open system test bench, I saw that it was actually, like, you see a lot of dehumidification capacity towards the very beginning of the reaction, which is as expected, as there's a lot of dry material that is wanting to absorb the water from the humid air. And then it begins to level out such that we're maintaining above 3.53 grams of water per kilogram of dry air coming into our reactor. And in addition to this, this is also reflected through the effectiveness. So it's actually pretty close to 1 right towards the beginning. So you get to around 0.85 effectiveness towards the beginning of this reaction. And then it begins to slowly progress as you're hydrating your salts. There's less opportunities for dehumidification due to there being less dry material ready to be discharged. So yeah, kind of interesting here, but in the future what we're looking to do is having this sort of like a desiccant wheel setup where we're able to constantly regenerate as well as dehumidify our airstream and look at how these thermochemical materials would react in this case. So with that, I wanted to kind of conclude my work. So as we see, commercially available silica salt composites that we have synthesized demonstrate good hygrothermal stability at the material scale as well as the reactor scale, as in there was no deliquescence at these higher humidities in comparison to what calcium chloride is capable of doing by itself. In addition to this, slight variations in the humidity conditions can significantly impact your performance. So when you're looking into incorporating these into buildings, we have to be really careful looking at the ambient conditions of the climate that you're investigating and how well it will perform in those regions. And the same thing goes for flow rates. Just slight variations here can result in significantly different behavior. And we're able to, in the future, we should manipulate the flow rates so that we're able to achieve what we want to for our thermal power outputs and temperature lists based on what our building is requiring. Finally, the dehumidification capabilities based on the absorption isotherms, as well as what we were seeing with the dehumidification capacity and the dehumidification effectiveness, are comparable to other desiccant sorbent materials at the material scale, and they do show high promise in the future for this system. So with that, moving forward, I'm going to be using this data to help validate some of the models that we have, such that we can come up with a more optimal design than this packed bed geometry. And I would also like to incorporate this data that I've gathered into building, eventually incorporate it into building level models so that we're able to look at the transient performance for this hydration process and how we can potentially incorporate this into an HVAC system. And so with that, I'd like to thank Dr. Ishita for her help with the material synthesis. I'd also like to thank Dr. Michael Adams, Owen Moran, and Stephen Zach for their collaboration throughout this effort and helping me continuously improve the open system testing the open system preconditioning system. So I was able to conduct these experimental tests. And with that, finally, I'd also like to thank the iBuild Graduate Research Fellowship for their funding and support throughout my PhD. And with that, I'm happy to take any questions at this time. Thank you.